接下来的场次，我们非常荣幸邀请到演讲嘉宾德州仪器 Jeff Marani 先生。Jeff Marani 先生将为我们带来题为“AI 资料中心的电力挑战与解方”的精彩分享。For our next session, it is our great honor to welcome our speaker, Mr. Jeff Marani, VP and Head of R&D, Kilby Labs at Texas Instruments. Mr. Jeff Marani will share his insights titled Reimagining AI Data Center Power Design. Ladies and gentlemen, please welcome Mr. Jeff Marani.
"25 years ago, an average data center rack consumed about 5 kilowatts of power. Now that's a lot of power. It's actually enough power to power 8 typical households here in Taipei. What did we do with this data? Fundamentally, if you think about it, we used this data to make our lives more productive. Instead of going to the bank, I can do online banking. Instead of doing regular mail, I can do email. We were able to accomplish more in our lives with the time that we have enabled by these data centers. Only 25 years later, last year, the world talks about 1 megawatt data centers. Now think about this. In the same form factor of a rack, we are now consuming 1 megawatt of power, enough to power 1,600 households here in Taipei. A lot has changed in the last 25 years. What hasn't changed is what this data does for us in our lives. It makes us more productive. Today, I can digest entire manuscripts at the tip of my fingers with the press of a button. I can write code in an hour. It used to take me a week. We can accomplish more as humans today with this data than we could without it. But this data comes at a cost. It comes with power, 1 megawatt of power. I think it's pretty easy also to imagine that in the future, we're going to have even more bits in our lives. These bits cost power. This introduces significant challenges in the industry, in the power delivery architectures, and in the ecosystem. And I'm very excited to be here today representing Texas Instruments and our contributions to this ecosystem and to the underlying technologies that we believe are necessary to enable these trends. So let's look at where this power is going. Where does the processor power go? There's actually 2 exponential trends that are taking place right now. The first is in the amount of current that the processors consume. 3-4 years ago, a high-end processor might have consumed 500 amps. Today, 2,000 amps is a real number. You can see in the plot, forecasts over 10,000 amps of current consumed by these processors. That is an exponential increase in the amount of current that the processors are taking. But that's only one of the exponential increases. The second one is how many processors fit into the rack itself. Just 3 or 4 years ago, a common number was about 40 processors per rack. Today, people are talking about over 500 processors per rack, a second exponential increase. The combination of the 2 represents a super exponential trend, and this is how you get to a 1 megawatt rack. Now, with both of those trends, you can imagine everything gets squeezed. The amount of space available inside these racks is shrinking for power management for other solutions to maximize the amount of volume or real estate that's made up from the processors themselves. That represents an immense opportunity, an immense challenge, and a limitation if we can't shrink the power, improve the power density inside of these architectures. So let's now go one level deeper. How is power delivered to these processors? Historically, LPD, or lateral power delivery, is how we delivered power to these processors. It was done with what's called a multi-phase switching regulator. Many of these surrounding the processor. The higher the current, the more of these that you need around the processor, and current flows laterally through the board, out of the power, and into the bumps of the processor. Now, if you look at an average solution today that uses an architecture like this, it actually takes more physical area for the power than it takes for the processor itself. Think about that. The power is taking more area than the actual processor that's doing the functions that make our lives better, that make our lives more productive. For this reason, and also for efficiency reasons, the world has migrated to vertical power delivery. Vertical power delivery is a radical change in the architecture where now the power delivery is placed directly underneath the processor and the current flows directly out of the power and directly into the bumps of the processor. Now, why do we do this? The most important reason I would argue that this is happening is because of power consumption. If you take an example of just a 1,000 amp processor and you imagine how much power is lost in the distribution of the current going out of the power and into the bumps of the processor, and you compare lateral versus vertical power delivery, you can actually save about 75 watts of power just by going to vertical power delivery for 1,000 amp processor. Now aggregate that across a 1 megawatt rack. Across a 1 megawatt rack, you can save 50 kilowatts of power by going to this architecture. Think about that for a second. 4 years ago, racks didn't consume 50 kilowatts. We're saving that much power by changing to this architecture. And this has happened. This isn't happening. This has happened. But with this comes enormous challenges. And if you combine the challenges with what we talked about on the first slides, space is a premium. A lot of times people will talk about surface power density, or amps per millimeter squared. How much physical area does the power solution occupy per unit current? And that matters because right now power is taking up more physical area than the processor itself. But if I want to squeeze 500 or more processors in a rack, the Z dimension matters as well. Amps per millimeter cubed matters as well. And especially if I'm going to put power on the back side, I have to do that not only in the form factor, the height required, but I also have to figure out how to get the heat out. These are real problems, these are real challenges, and they require technology, they require innovation, they require rethinking data center architectures. Now this is at the processor level, but let's talk about the infrastructure level. Let's think about how power goes from the grid all the way to the gates of the processor. Today, this architecture has changed. What it used to look like is an AC to DC conversion to a 48-volt backplane up the entire rack of the processor, 48 volts. That worked fine until we needed a 1 megawatt rack. With a 1 megawatt rack, that would require over 20,000 amps of current up the backplane. Unfortunately, the laws of physics are real and it doesn't work. And so out of a matter of necessity, not out of a matter of new ideas or just being neat, out of a matter of necessity, the world has shifted to a high voltage DC architecture. Either 800 volts or plus or minus 400 volts distributed up the backplane of the rack. This does conceptually solve the current problem. You can deliver 1 megawatt in a rack with an 800 volt backplane. But what does it do? It introduces new challenges. Now every tray inside the rack has to have an 800 volt converter. This space is super premium. And now we have to introduce an 800 volt DC to DC converter stage in addition to all the other power conversion stages that are needed for the vCore. You can see an architecture here where people will go from 800 to 48 volt to either 12 or 6, and then the 12 or 6 goes to the multi-phase VRs we talked about on the previous slide. That's how current is delivered to the gates. Now, it's not just about grid to gate. It's also about grid to light. And I think it's been very clear here at Computex this year how important silicon photonics is to the future of data centers in scaling up. These also have to undergo architectural shifts. Historically, the optics engines were powered from 48 volts, a number of DC to DC conversion stages leading to a 3.3 volts. The pluggable modules plug into 3.3 volts, and then there's some power conversion inside of there. Now, if you've seen a pluggable module, you know how small they are. These are super space constrained as well, and they are also undergoing a similar trend. Gen to gen, the current consumption in optical modules is increasing at an exponential rate. Now, the 48-volt backplane is gone. What do we do? 800 volts is up the backplane. Grid to light architecture also has to change. It has to change not only because of the 800 volt backplane, but because 1.6T to 3.2T to 6.4T optics requires gen to gen more power. And so the grid to light image here shows 800 to 48, 48 volt to 12, and then 12 to the optics. Why 12 instead of 3.3? Because there's more power. You can't handle the current through the connector at 3.3 volts anymore. The voltage goes up. Now, I want to take a step back because these are the architectures today. I'm not actually talking about the future. This is happening now. But what should the future look like? Let's imagine that for a second, and let's just take a step back and look at both grid to gate and grid to light. There are a lot of power conversion steps in series here. Why do we need that? Well, fundamentally, we need that because we need new technologies to imagine a better way to do this. And it's so important in the face of the challenges of power density and the amount of power and the limited real estate that goes into these racks. What if we could develop new technologies, new products that enable us to do things like this? Why do I need to go from 800 to 48, then 48 volt to 6, then 6 to core? Why can't I go from 800 to 6 directly? I eliminate a conversion stage, I improve system efficiency, I go from 6 volts to core, I get a much higher density, much higher power efficiency solution. Oops. That is a challenge. That is not a solved problem. The reason it's a challenge, the reason it's not a solved problem, is because we don't have all of the technologies necessary to enable this today. That's our job. That's the job of the room. That's the job of the ecosystem. Similarly, on grid to light, I go 800 to 48. Why can't I plug 48 volt directly into the optics engine? Because it's too big. A 48 volt DC to DC converter is too large. Sorry. A 48 volt optical engine is too large. I need it to be higher power density. I need it to fit in a super size constrained optics engine. This is the vision that we're driving with our partners and with the ecosystem at Texas Instruments. Optimizing power technology to enable us to eliminate or remove power conversion stages. So let's now go step by step, and I want to start with just technology. If I start with just technology and think about the foundation, or what I like to call foundational technologies, what is needed here to enable these trends? Well, let's talk about power FETs first. This is the power FETs that are used to provide the multi-phase power. The more current, the more of these you need. And typically there's two power FETs and a gate driver. More of those, higher current, fewer of those, less current. There's two technologies in the ecosystem today. There's discrete FETs that get co-packaged together, and there's monolithic solutions. About 7 years ago, Texas Instruments made the decision to transition to a monolithic power stage solution, and this slide attempts to explain why. There's really three vectors here. The first is reliability and performance, efficiency. How do I get to higher efficiencies while maintaining or improving reliability? When I do a power stage monolithically, I have very tight control of these power FETs. I can switch them very fast, I can keep them safe. It's a very, very reliable and high performance solution. What about thermals? With the monolithic power stage, I have an entire die, single die, that has all of these components on it, and I can expose that die to the back side. I can attach a cold plate directly to it, and I can pull the heat directly out of it. You can get a much more advanced and capable thermal solution going monolithic. The third, and maybe the most important, is architecture. Within the architectures, most of the power stages today are single phase, which means that there's one power stage, one phase in a package. What if I want to build a dual? What if I want to build a quad? Monolithically, that is readily accessible. With discrete FETs MCM'd, it becomes enormously complex. So for these reasons, we've transitioned to the monolithic power stages, but let's talk about inductors as well. Power modules, where you have these power FETs plus inductors integrated, is a trend. And the reason it's a trend is because people need to go to higher current per millimeter squared. Now, the way that people typically do that today is they take discrete or off-the-shelf inductors and they co-package them with these FETs. That works, but my argument here is that it's 1 + 1 = 2. You can see the discrete inductors there, and you can think about the amount of volume that this package takes up in terms of magnetic material. What percentage of volume in the package is made up of magnetic material? You can see it's somewhere 30, 50%, depending on the architecture. 1 + 1 = 2. For these reasons, TI invented, about 3 or 4 years ago, what we call MagPack technology. And the big advantage of this, conceptually, is that it enables us to flood 100% of the package volume with magnetic material. What does that give? It gives higher efficiency, higher power density, and we can enable some of the trends that we're talking about here from a fundamental technology perspective. Let's go to the 48-volt bus. We talked about 48 volts specifically for optics as a future. What do we need to do here? GaN is a very competitive power switch in terms of frequency, in terms of switching losses, in terms of power density, even at 48 volts. But my argument is that GaN discrete does not get entitlement of these GaN transistors. In order to really get to the ultimate power density, you have to integrate the GaN FETs with the gate drivers, just like we talked about with the power stages on the previous slide. And so for that reason, TI does not do discrete GaNs. We build integrated GaN solutions because that's how you get the most out of the GaN transistors. That's how you get to the power densities you need to get to. And there's proof. Discrete solution, integrated solution, 2 power FETs in the gate driver integrated with a GaN half bridge, or what we call Dr. GaN. 65% smaller semiconductor area, 33% higher power density. These are enabling technologies. These are things that enable us to get to more bits in our lives, to higher power racks. Let's go to the 800-volt bus, the famous 800-volt bus. GaN actually plays a huge role there as well, and it's actually the same opportunity. Discrete GaN cannot get to the entitlement of the GaN transistors at 800 volts that you need to get to the massive power densities that are needed for 800-volt converters. Integrated GaN is our solution. GaN with our gate drivers integrated into the package. 800 volts, though, is more than a device. It's a system. Every millimeter squared counts on these 800-volt boards. So what about bias supplies? There's bias supplies all over the 800-volt systems, isolated bias supplies, safety isolated. 800 volts is a high voltage. About 7 years ago, TI embarked on a journey to develop isolated bias supplies where all of the isolated power is integrated into the package. And over the years, we've gotten better and better at it. We start out at 5 volts and 500 milliwatts in a large package. Today, 20 volts and 1.5 watts, 3x higher power. This saves millimeters squared on an 800-volt board that enables us to get to the power densities that are required to enable this backplane. What about high voltage sensing? I have to sense high voltage. I have to use it to detect, to protect. Why can't we integrate that as well? TI has capabilities that enables us to do that with 15x smaller area than the competing solutions. And again, every millimeter squared counts. So I hope you got a picture for now of the technologies. This is really the foundation. But the technologies don't mean a lot unless you have products that can use them, products that can benefit from them. So let's now go back through the chain and let's look at how these technologies can enable products. Let's start, again, at the multi-phase power for the processors. This is a real example, real data, showing the benefits in a 4x6 common footprint power stage of a monolithic solution versus a MCM solution. The ringing is 10 volts lower, enabled by the monolithic solution. That gives you better reliability, we can switch faster, we can enable higher efficiency. What if we go to architecture changes and thermal enhanced packages? This is a 5x5 dual power stage, 2 phases inside of a single die, common footprint, and you can see it's got a top exposed pad. This enables us to further improve the power density and reduce the temperature rise of the devices themselves because all the heat can flow out the backside. Now, both of these devices run at 12 volts. We're talking about 6-volt architectures as well. Why 6 volts? Well, 6 volts enables us to do amazing things when it comes to shrinking these power solutions and enabling the power density. This is the same package, same footprint, 12 volts versus 6 volts. We're able to switch at 2x higher frequency and improve the efficiency by over 3%. Now think about that. 2x higher frequency and higher efficiency enabled by all of these factors: monolithic power stages, 6-volt intermediate bus, top exposed pad. These are the types of capabilities, the types of products that get us to the future that we need to get to. But these are all power stages with inductors side by side. What about modules? What about integrated solutions? How do I get to the next level of power density? 2 amps per millimeter squared is needed today. This is not a 2-year problem. This is a today problem. How do we get there? Well, we get there through integration, and we get there through 1 + 1 being greater than 2. So for that, I'm very excited to announce TI's next generation power module, a 9 by 10 by 5 millimeter 4-phase power module. You can see dual phase power stages. You can see a large magnetic that enables us to fill the package volume with magnetic material, and you can see package thermal enhancements. This is greater than 2 amps per millimeter squared, and it's an industry leadership device. Now I know what everybody's thinking. It's a cartoon. It's actually not. We have the device. 280 amps peak current handling capability in this package. This is 1 + 1 is greater than 2. This is how you connect the technologies. This is how you start to combine the base foundation to enable these architectures. What about 800 volts? I think we now understand why 6 volts is an important architecture, but how do I get from 800 to 6? Well, the way you get from 800 to 6 is actually very similar conceptually. This is TI's 800 to 6 direct conversion device. You can go to the booth and see it for yourself. It's there. 20 kilowatts, 6.5 millimeters thin. How do we get to this? We don't get to this with just a GaN transistor. We get to this with integrated GaN devices. We get to this with integrated high voltage sensing, with integrated bias supplies. We get there with digital controllers. You can't just do one thing. You have to combine technologies, combine products, combine innovations. That's how you get to something like this that can fit all of the power you need in the form factor required. Now, why does form factor matter here? Let's look at a cartoon here of a hypothetical GPU. Let's look at our board. Where does it go? Now remember, the backplane is 800 volts. All of the cards that plug in would plug into 800 volts. That's the vision. How do you get there? Well, you have to plug this thing in, and you have to plug it in as close to the processor as possible, because now we're distributing 6 volts and it's very high current. You want that to be as close physically to the processor as possible. That means it's got to be super high power density, it's got to be super optimized, and it has to be thin, because we're trying to pack more processors in the rack gen to gen. This is how this form factor was designed, and it fits. This fits into the examples of these types of solutions that we've seen in the market. Let's go to optical modules. I mentioned MagPack, and I mentioned how 1 + 1 is greater than 2. Let's see some real-world product examples of what that means in optical modules. Now remember, optical modules are super size constrained. The optics engines are getting higher power, and the space is not growing. This is an example of a conventional 6-volt, 6-amp module. This is 1 + 1 = 2. This is the MagPack version. 57% smaller, much higher efficiency, same current rating. That is what this technology enables. Let's look at another example. This is a 16-volt, 3-amp module. This is the MagPack version. 55% smaller, 2 to 6% higher efficiency. These are game changers for optic modules, and nobody else has this technology, nobody else has these products. Where do we go from here? Because these are available today. These are being used and ramping today. Well, why can't I do a 12-volt, 50-amp module? Optics modules are going to need it. The current goes up, the requirements go up. Why can't I do a less than 1 millimeter thick module? Nobody has those. Height matters. MagPack enables that because I can flood 100% of the package area or volume with magnetic material. What if I go to 48 volts? We talked about 48 volts in GaN. Why can't I build a 48 volt GaN module that combines the GaN technology and this magnetic packaging technology to enable a 48 volt solution that's small enough to fit into the optics engines? Those possibilities are within our reach now. The technologies that we've invested in, the capabilities that we've developed, enable these futures for both optics and also for gates. So let's now take a step back, because I think it's amazing to think about it, but these are not 5-year roadmaps. These are happening now. And the world of data centers in the pace of development is unprecedented. It's perhaps the most exciting time in my career, the most exciting time for power engineers, because these technologies are not nice to have. They're must-haves. And if you have solutions, people will adopt them immediately. That tells me these are real problems. But where do we go from here? Well, you could see integration is the theme. In order to achieve these solutions, in order to solve these problems, you have to integrate. You have to integrate GaN devices with the drivers. You have to integrate more and more phases per power stage. You have to integrate magnetics in an optimal way within the power modules. Better magnetics is a part of our future. We didn't talk about it much today, but capacitor integration is a key enabler to getting to higher frequency and higher power density. We talked about GaN, but we didn't talk about GaN at lower voltages. GaN is very, very well publicized at 48 volts and 600 volts, 800 volts, 1200 volts. 20 volt GaN does have advantages. It's a faster switch, it's a higher density solution. Why can't we use that as well? These are roadmaps, these are technologies that are actively in development, and they're in development because they solve real problems. What does that look like? Let's use a couple of examples where we can pick a few of these technologies and combine them to see what it gives us. How about a greater than 2 amp per millimeter squared, 2 millimeter thick VPD module? For those of you who are familiar, the best thickness VPD modules in the world today are anywhere between 4 and 5 millimeters thick. That is state of the art. Why can't we use these kinds of capabilities to build a 2 millimeter thick module that's greater than 2 amps per millimeter squared? You can see a cartoon and you can see a prototype. These are not fantasy technologies. These are things that are in active development because customers need these capabilities. What about IVRs, or integrated voltage regulators? I go to a 10,000 amp processor. I'm going to need an outstanding number of bumps to get 10,000 amps into that processor. It becomes unrealistic. The solution to that is integrated voltage regulators that are integrated inside the ASIC package. You can imagine, I talked about how much power density matters outside the board. When you start putting power converters inside of GPU packages, the solution size and power density becomes exponentially more important. But if you can do that, you can reduce the current into the package. And at a 10,000 amp processor, I would argue that a 1.8 volt IVR is insufficient. It only reduces the current by a factor of 2.5. For these reasons, TI is developing technologies that enables higher voltage IVRs, high frequency, high voltage, and this is a tough problem. But these are needed technologies to enable 10,000 amps or higher processor current. So with that, I hope you got a good sense for the trends that we see, what's driving those trends, the technology, the foundation of the investments that we've made, and the products that are coming or are already here to try to enable these architectures, to enable a 1 megawatt rack, 800 volt to 6 volts to core, with a lot of supporting technologies necessary. With that, I thank you for your time. I thank you for your attention. I hope you enjoy the rest of Computex. Enjoy your time.
感谢 Jeff Morani 先生精彩的分享。接下来是中午休息时间，主办单位特别在场外休息区为各位嘉宾准备了精致茶点与轻食，诚挚邀请大家前往享用。